Hi everybody. In this video we begin with Chapter 6, Trigonometric Functions and Equations. Specifically with Section 6.1, Angles, Circles, Arcs, and Sectors. So we begin with some illustrations here to clarify questions regarding vocabulary. So when we talk about angles, we are going to be measuring angles counterclockwise. That is, from right to left, as you can see on Figure 6.1. Where we have some angle components. So if this is the initial side, in positive terms, the angle is measured counterclockwise. Then where the angle ends is what is called the terminal side. And if we were to measure an angle in opposite direction, notice that here we have this angle, outer angle, measured in opposite direction. This angle would be negative. And not only would it be negative, but it would be equal to theta minus 360. Notice that the point where the terminal and initial sides meet is known as the vertex. In figure 6.2a, we're going to see the standard position of an angle on the Cartesian plane. So notice that the initial side is the positive part of the x-axis. And then this is where we start measuring it to whatever the terminal side would be. Again, counterclockwise. In figure 6.2b, we have coterminal angles. Now, you have a Cartesian plane and you have an angle alpha that is measured from right to left or counterclockwise. This would be a positive angle. And then you also have angle beta, which is measured clockwise, and they both meet at this terminal side here in blue. Now, these angles are obviously equivalent, but they would be different in sign. Also notice that beta would equal alpha minus 360 degrees. One last thing is the Cartesian plane. We have 4 quadrants, 1, 2, 3, and 4, and they are numbered counterclockwise as well. So now let's take a look at the geometry of a circle. And basically, we're going to look at some vocabulary here. So notice that we have a center for a circle. This is known as the center. Then from the center to the outer edge of the circle would be the radius. This is a central angle. Then if we have a sector, it's this green area. The sector would be this area here. This part of the circumference is known as an arc. Then if we cut the circle on a side, we would get a segment. And the line that cuts the circle is known as a chord. Also, we have to be able to differentiate between a circumscribed circle and an inscribed circle. So notice that a circumscribed circle, in this case of a regular polygon, is a circle that goes through the vertices of the polygon. And then an inscribed circle of a regular polygon, in this case, the radius is perpendicular to the side of the polygon, and you're going to have points of tangency with the polygon. In the next slide, you're going to find figure 6.3, where you have different circles with the same central angle theta, subtending different arcs, but the ratio of the arc length to the radius, S over R, remains constant. In other words, if we take the first circle, the first arc over the first radius is going to equal the second arc over the second radius, and this is equal to the third arc over the third radius. Now, obviously, the reciprocals would also be true. The ratio S over R indicates how many radius lengths R fit into the length of arc S. For example, if S over R equals 2, then the length of S is equal to 2 radius lengths. This accounts for the name radian. So this would be 2 radians. Now, another thing that is important is distinguishing between major and minor arcs. If a central angle is less than 180 degrees, then the subtended arc is referred to as a minor arc. If the central angle is greater than 180 degrees, then the subtended arc is referred to as a major arc. Also, 1 radian is a measure of a central angle theta of a circle that subtends an arc S of the circle that is exactly the same length as the radius. So in other words, S over R would equal 1, which means that theta is equal to 1 radian. So next we're going to talk about the unit circle. When an angle is measured in radians, it makes sense to draw it in a standard position. It follows that the angle will be a central angle of a circle whose center is at the origin. As we saw in the previous slide, it makes no difference what size circle is used. So the most practical circle to use is a circle with a radius of 1 unit, because then the radian measure of an angle will simply be equal to the length of the subtended arc, as we see here. The circle with a radius of 1 and a center at the origin, 0, 0, is called the unit circle, as we can see here. The equation for the unit circle is x squared plus y squared is equal to 1. Because the circumference of a circle with a radius r is 2 pi r, so this is a circumference. But in this case, because the radius is 1, the circumference is going to be 2 pi. Now, a central angle of one full anti-clockwise revolution is 360 degrees, and it's going to subtend an arc on the unit circle that is equal to 2 pi. Therefore, 360 degrees is equal to 2 pi radians. It follows that 180 degrees is going to be exactly pi radians. So this fact can be used to convert between degree measure and radian measure. So next we have example 6.1, and it says, convert 30 degrees and 45 degrees to radian measure and sketch the corresponding arc on the unit circle. Use these results to convert 60 degrees and 90 degrees to radian measure. So recall that we said that 180 degrees is equal to pi radians. Therefore, that means that 30 degrees is equal to 30 times pi over 180 degrees, and this is going to give us pi over 6 radians. Likewise, 45 degrees would be equal to 45 degrees times pi over 180 degrees, and this is going to give us pi fourth radians. So this is what it would look like on the unit circle. So notice that 30 degrees is equal to pi sixth radians, and 45 degrees is equal to pi fourth radians. Next, they want us to use the results to convert 60 degrees and 90 degrees to radian measure. But notice that 60 degrees is simply going to be 2 times 30 degrees. So that means that 60 degrees is the same as 2 times pi over 6, which is going to be pi thirds. And then 90 degrees is equal to 2 times 45 degrees, which means that 90 degrees is equal to 2 times pi fourths, which is going to be pi half radians. So next we have example 6.2. Part A says, convert the following radian measures to degrees. Express them exactly if possible. Otherwise, express them accurate to 3 significant figures. So number 1 for part A is 4 pi thirds. Now there's several ways to do this, but notice that this is the same as 4 times pi thirds. And we already said that pi thirds is 60 degrees, so this is 4 times 60 degrees, which is going to give us 240 degrees. For number 2, they have minus 3 pi halves. Again, this is the same as minus 3 times pi halves. And we said that pi halves is 90 degrees, so this is minus 3 times 90 degrees, or negative 270 degrees. For number 3, they want us to convert 5 radians to degrees. So notice that this is the same as saying 5 times 180 divided by pi, and this is going to be approximately 286 degrees to 3 significant figures, as they asked us to do here. And then number 4, 1.38 radians. This would be the same as 1.38 times 180 over pi, and this is equal to 79.1 degrees to 3 significant figures. So now let's do part B. So for part B, they say convert the following degree measures to radians. Express them exactly. So for number 1, we have 135 degrees. This is going to be equal to 135 times pi over 180. And this is going to give us exactly 3 pi fourths. For number 2, negative 150 degrees. So this is negative 150 times pi over 180. And notice that this is going to give us exactly minus 5 pi over 6. For number 3, 175 degrees. Again, 175 times pi over 180. And this is going to be exactly 35 pi over 36, which is approximately 3.05 radians to 3 significant figures. Then for number 4, they want us to convert 10 degrees. So this is going to be 10 times pi over 180. And notice that this is going to equal pi over 18 radians exactly, which is approximately 0.175 radians to 3 significant figures. So next we're going to talk about the concept of arc length. Notice that for any angle theta, its radian measure is given by theta is equal to S over R, arc length over radius. Simple rearrangement of this formula leads to another formula for computing arc length. So that means that the arc length is equal to theta times the radius. Now it is very important to notice that theta must be in radians. So let's take a look at example 6.3. And it says, a circle has a radius of 10 centimeters. Find the length of the arc of the circle subtended by a central angle of 150 degrees. So the first thing we need to do is convert this to radians. So again, 150 degrees is equal to 150 times pi over 180. And this is going to be 5 pi over 6 radians. So then that means that the arc length is equal to 5 pi over 6 times the radius, which is 10. And this is going to be 25 pi thirds, which is approximately 26.2 centimeters. And this is rounded to 3 significant figures. So next we have example 6.4, and it says, the diagram shows a circle of center O with radius R equal to 6 centimeters. Angle AOB subtends the minor arc AB, such that the length of the arc is 10 centimeters. Find the measure of angle AOB in degrees, accurate to 3 significant figures. So recall that we have that theta is simply going to be the arc length over the radius. So in this case, it's going to be 10 over 6, which is 5 over 3 radians. But we need to convert this to degrees. So this would be the same as 5 thirds times 180 degrees over pi. And this is going to give us approximately 95.5 degrees, accurate to 3 significant figures. So now we're going to talk about the sector of a circle. So a sector of a circle is the region bound by an arc of the circle and the two sides of a central angle, as we can see in this figure. The ratio of the area of the sector to the area of the circle is equal to the ratio of the length of the subtended arc to the circumference of the circle. So that's what we see here. The area of the sector over the area of the whole circle, pi r squared, is equal to the length of the subtended arc S to the total circumference, 2 pi r. So if we solve for A, we're going to get 1/2 r times S. But from the formula for arc length, we know that S is equal to r pi. So if we plug that back in here, we're going to get that the sector of a circle is equal in area to 1/2 r squared times theta, where theta has to be in radians. So now we're going to do example 6.5, which will be the last one on this video. And it says, a circle of radius 9 centimeters has a sector whose central angle measures 2 pi thirds. Find the exact values of A, the length of the arc subtended by the central angle. So remember that the length of an arc is simply going to be r, the radius, times theta. So in this case, it's going to be 9 times 2 pi thirds, which is going to be exactly 6 pi centimeters. For part B, they want us to find the area of the sector. We just said that the area is going to equal 1/2 r squared times theta. And then in this case, 1/2 times 9 squared times 2 pi thirds. And if we do the math here, this is going to give us exactly 27 pi, in this case, centimeters squared.